Okay, so we're done with the with this part, which is just about entirely about limits. But don't forget that apart from this, very last topic, limits at infinity, infinite limits at infinity. It's all about continuity, really. Um, Continuous functions, even when they're continuous, they might have some behaviors at infinity, uh, but um, but really, all the computations of limits will lead to applying continuity at some point. So the list of continuous functions has to be remembered, and so that's how we pretty much compute limits anyway. So we'll be revisiting this more than once, but at this time we turn to the proper calculus proper is what I'm saying. Okay, I want to start a new one. No. Okay. Just a minute. Okay, so calculus proper simply means that we're turning towards something that is how the calculus appeared and why it was called calculus rather than the theory of limits. So a lot of people actually disagree with me on that, and they will say that the essence of calculus is limits. Okay, so I write it down so to give credit to those people, even though I disagree. So the essence of calculus is limits. Okay, so I think calculus is more about change and rates of change and measuring change and comparing change rather than studying limits. You get to limits later. Once you set everything up, you can now turn into to limits to actually figure out certain things that are with infinite accuracy. So you start with just the best you can do, evaluating rates of change, for example, and then at the end you with the limits you can actually make that step from average to instantaneous. Okay, so the essence is change of what? Naturally of functions, and there appear that the change in the rates of change appear very early. It is actually I believe I did bring it up early on in the class, and that is as always the origin of calculus, and we sort of trace it back inevitably. It is the time versus space. So change of location versus change of time. Okay, so there you go. It comes up on a very simple simple circumstances. That is something that I brought up before. That is the broken speedometer situation. In broken speedometers, when you are asked to evaluate your speed when you don't have a speedometer. So the answer is, what to do, and the answer is use your odometer and a watch. Okay, so why? Because we know speedometer, we know the meaning of speed, and it is in fact what's speed. Distance over time. So distance over time, and more precisely, is change of location over change of time. Okay, so there you go. So that you can evaluate that as many times as you like during your trip. That little evaluation, because change of location, that or the odometer will give you that. The odometer gives you the location, and therefore you with a little with a piece of paper you can compute the change, and with the watch you know how much time has passed. Okay, so I have this example of just to make a number slightly more specific. Say you drove, so you look at odometer. And you literally subtract. So you have 10,000 miles on your odometer, then 10,000 miles, and 10,035 the next, and then 10,100 or something like that. Okay, so these are your readings, and then and they say you do readings at in the beginning, then after 1 hour, and after another hour. Okay, so and then you just that plan that we have here to describe speed as a change of location, change of time. Well, that's you trace the change of location, and this will be change of time. So if you do it regularly, then the change of time will be always the same. It is 1 hour. Just if you want to keep it simple. But that's your during the first hour. That will be your estimate. Once again, change of location over change of time. So you will be 10,035 minus 10,000 divided by, say, 1 minus 0. Okay, so you have a watch, and well, in fact, you can say you start at noon, and then 1 p.m., 2 p.m. Okay, so that's and then you actually have to literally compute the time by doing subtraction. So you certainly can have a clock, but to keep it straight, we want to be specific about what is that we're looking at. What are the quantities that we're tracing? And the quantity we're tracing is not really how time much originally. It's not how much time has passed, but rather it is time as it is on the clock and the location as it is on the odometer. So these are the two quantities that we take into account, and then we take those quantities and put them in this little formula: change of location, over change of time, and that gives me the speed, or also known as the average velocity. What's the difference between speed and velocity?
Speed is a direction.
Right, so direction given by what? By the sign, positive, negative. That gives you the direction. It's actually very important because to remember about this direction, because for as long as you're driving on a straight line, it's fine. It's positive or negative. You're moving towards some previously chosen positive direction or destination, or you're moving in the opposite direction. Then you move on actually to moving any planetary motion or any kind of missile or whatever. There are infinitely many directions, so that's why speed becomes so much less important in comparison to velocity. So that's why we never just look at how much I have covered of the distance. It is the proper term for this for change of location is the displacement, and the displacement is the change of location, which the last location minus the previous location, in that order. You don't try to turn them around so that you would end up with a positive number. If it's negative, it's negative. Okay, so and certainly if you just put it on a piece of paper where your odometer readings, well, odometer reading, actually there's a limitation to odometer reading because it's always will be positive. It's not technically displacement unless you keep driving in the same direction. Let me finish this example, but it's certainly worth mentioning. Yeah, the 2 minus 1. Okay, so let me finish this computation. This one will give me 35 miles per hour, and this will give me 65 miles per hour. Okay, so the odometer, the odometer, why we have to be careful about using that, because odometer readings grow always. So you cannot, it does not go down ever unless you tweak it. A better measurement would be actual like milestones. So then you can turn around, record how many milestones has passed, and then you that will potentially give you also, if you at some point you turn around and start driving backwards, you're still okay. You still all the numbers will still work out. So that's option number 1, milestones. Milestones or just coordinates. So if you do it by hand, that's milestones, but if you have a GPS, they will give you the coordinates, and at the same time, that's how do they possibly compute your speed anyway? Your GPS, whether it is iPhone or it is actual dedicated unit, they give you the speed, and they will sometimes tell you that you're speeding. How do they know? Well, they know your location, and then next location after, say, a second, your unit knows, actually, not the satellite, but your unit knows 2 readings consecutively, two coordinates, and then it does exactly this formula. Subtracts 2 consecutive locations and divides by the time that has passed. Okay, so the accuracy is not very high, but it's pretty good, I think, from my experience. So either way, just imagine that that's what's happening, and it is always average velocity at the end. Okay, so we could certainly do it with the next level of this. If you do it by hand, next level. So by hand, the next level is Excel. Okay, with, I don't think I did it right. Yeah, so more data. So we'll do that later on, but this time there is the next step. So the Excel will give us more data. So if you collect more data and you collect more and more data and more frequently doing it, then by hand, applying this formula by hand becomes impossible for the most part. And then the next one is we take the limit, and we will end up with the instantaneous velocity. Okay, so the point of instantaneous velocities is more theoretical. So I mean, if you want to know your speed, it doesn't really matter. It doesn't have to be instantaneously correct, unless you hit the wall and you know what exact at what exact speed that has happened in that exact moment. Otherwise, if you just want to know roughly where you are, you just increase the accuracy to the degree that you need. That's it. So you don't have to actually go all the way to the end of that limit process. Remember, limit is what's behind the limit is infinitely long process, or infinitely many steps that you take to get there. You never need infinitely many. But in theory, if you're doing any kind of theory, planetary motion or just object motion moving through space, through air, and then there is a gravity, and there is a air resistance, and there is a spin. All of that, if you want to solve the problem with absolute accuracy, so that you can freely develop the theory and not wondering what is that accuracy of my theory, then yeah, you need instantaneous velocity. You need everything pretty much instantaneous. You assume that you know your location instantly with absolute accuracy, and then same for time. Then you can compute those fractions that are called difference quotients, and then you take the limit and you have your instantaneous velocity at that moment, not over a period of time. So all of these are computed. If you keep going with these, they are limited to that time interval that you have chosen. You can have many intervals, you can make them shorter, from 1 hour to half hour to 1 minute, 1 second, but unless you actually apply limits, they will remain average velocities, and they are limited to an interval of time, not an instant. So velocity average over a period of time. So once again, the correspondence then is between intervals and those numbers giving you the velocity. Instantaneous velocity, it is a single moment or instant. So at each moment you will have velocity, and just like your location is changing continuously, your velocity will be also changing continuously. So think about an object thrown in the air. What's going to happen? It will be slowing down continuously, not incrementally, continuously, and then it will start falling down, speeding up once again continuously. Okay, so you can learn that. You can actually have the precise formula. You know, everybody knows that it traces out a parabola. Okay, so how do you know? Well, not an approximately parabola, but the exact parabola. Why? Well, if you you'll need absolute accuracy for that, and you can only do that through limits. So let me say a couple of words more about what we care about instantaneous velocity. Well, let me do it later. Let me do the Excel. So as we have been doing it, okay, so if I just can remember what the name of the file was. Maybe. Okay, so what I want to do is, in addition to that, actually, so remember the last time we used the Excel. It was for remember what it was? It's not this, not that. Scatter plot, perhaps. It was a few days ago. Not this one, not that one. This one. No, it's not this one. So we were doing motion. Remember motion discussion of. Did we discuss motion?
I don't think so. This file.
So the other class. Sorry about that. Yes, that sometimes you wonder. So okay, that's fine. So we're starting from scratch then, and what I want to do is what I just described as far as the motion in driving motion is concerned. But this time, let's do something slightly more complicated with more points in plotting. Okay, and we'll see how one thing depends on the other. So I'll start with something that we have done already, and that is just the location. Okay, so I'll put here, let me put it here as I always do. So this will be time, and this will be location, and okay, so and the location depends on time, which is what we just did. So location, time measured to time of the day, okay, to literally what the clock says, but we could certainly start with 0, and then location depends on the time. Somehow we have collected that information. Okay, so as always, I put h here, my constant, 0.1 second. Okay, so I will add equal to the previous plus R1, R2C1, R2C1, okay. So my time, R2C2, I'm sorry, R2C2, okay. So my time progresses 1/10 of a second at a time. Okay, it is. And now location, I'll pick a formula that is really not important. I'll put something complicated here so that we wouldn't think that there is any kind of particular formula that is preferable over any other formula. Okay, so I'll put here just a formula. How about sine? Why not? Sine with, how about x sine x? Okay, so this plus sine of that. Okay, why not? Okay, okay, so I spread it. So these are my locations. Okay, so I'm plotting it. Location is a function of time, so where we are after 2.3 seconds, we're going to see it from my chart. Okay, so this one. Okay. So horizontal axis is time, vertical time is location. So not too quickly, we have moved in 2.5 seconds, we have moved 3.5 feet. Okay, so that's fine. Now what about now? Let's talk about the velocity. Okay, so periods of time. So I have like I don't know, 26 to 25 points, I think, and but there only will be 24 intervals. So over those 24 intervals, I will be computing average velocity. Okay, so at the end of that period, so as you can see, I skipped the first moment of time and I moved directly to point 1. Okay, so now I'm computing just look at that formula over here. Change of location over change of time. That's what I do. Okay, so watch carefully. Not that complicated at all. What's going to happen? So I'm writing equal to now change of location in the numerator. Okay, so current location, okay, minus the previous location. Okay, current location minus previous location, blue minus red, divided by, and now current time minus previous time. Okay, is it large enough? The formula, I could make it larger. Yeah, so that's the formula, as you can see. So once again, we are computing along the row. We take into account two entries in the location row, and then 2 entries in the time row. I'm sorry, column. Okay, and then so we subtract vertically previous. Current minus previous. Okay. So as you can see, that is the velocity that I'm seeing just too many digits here. So let me cut it down. Okay. So that's what has happened during that period of time, during the first 0.1 second period. We have covered. Look at it. We have covered about. Why is it so inaccurate? Why is Look at it. It should be 0.2 minus 0 divided 0.1 minus 0 should be exactly 0.2. But as you can see, there is some problem with accuracy. Yeah, that's what it is. 2 minus 0, right? We'll just verify. Look at the numerator, 0.2 minus 0, and then 0.1 minus 0.
I think it's because you simplified it. It's supposed to be more decimal points for the time and location, possibly.
No, you see, it only displays these. Okay, so let's verify. Let me give you more digits. How many digits it displays really has nothing to do with the. Yeah, is it this one? I see. Oh, okay. So yeah, right. So it's not a mistake on the right. It's a mistake on the left. So that's a lack of digits. It's not 0.2 for one reason, because it is not a straight line. If it was a straight line, that's where we would see the difference. Okay, great, thanks. Okay, back. Okay, 3 is enough. So we have covered roughly 2 feet in that 0.1 second. Okay, so and then I do the same for every single one of them, and you can see a pattern probably. Okay, so what's happening? What's happening? What? It is slowing down. That's right. It is slowing down, and you can actually ask yourself what is in the graph. So the graph is not of the velocity. It was built entirely about location versus time. So where is that observation is visible on the graph? It is slope is decreasing, right? So the time change intervals is the same exactly, but the growth is smaller. Okay, so to see that it is indeed the case, let's plot velocity versus time. Okay, so I'm doing time and velocity separately, and we're plotting this thing once again. Okay. So that is the new function. The first function was the function of the location. The second one is the function of the velocity. It very conveniently highlighted the intervals that are involved. The purple one is the x-axis, and the blue one is the y-axis. So as you can see, the two functions actually do not resemble each other in any way, but you do see that there is a decline, what was verbally described as the car is slow, or whatever, the object is slowing down. Firstly, the slope is declining. Now you can see a function that is declining. So that function on the right is the function of slopes. So that difference quotient that we just looked at, we not looked at, we built into this computation. It is the slope, right? So there are 2 points. Those 4 numbers are 2 points. And we just, as if we draw a straight line through those points and just look at the slope. So that's what we did. So that is the essence of calculus. As to, from a function, we build a new function by looking at its slopes. And it tells you a lot about the original function. So remember that just the problem we started with. If you don't know the velocity, what do? That's what you do. You compute it from your odometer. So location gives you the column location. It gives you the displacement divided by the change of time, and that fraction gives you the average velocity. So let me. Even though the location might be exact, the velocity is inevitably approximate, because as the interval gets shorter and shorter, that becomes the accuracy becomes better and better. So, for example, I could make it the same if I put 0 here. You see what has happened? What has happened? Look at what happened to the graph, or the first graph.
The intervals are shorter, so it's showing less change in the slope.
From one to the next, right? And so it is, in fact, looks like a straight line. It looks like a straight line, right? Because the intervals are so short, then the change of the slope is invisible, and looks like a straight line, but it is not a straight line, as we can see on the right. Because the Excel resizes it, even though the change, look at the y-axis on the second graph, the value changed very little, but because Excel resizes the graph, and it is actually very visible that there is a change of the slope. Okay, so that's roughly how it works, how we produce velocities. More interesting, let me go in the opposite direction. What if I put a 5 here? So this was zooming in. Remember, that will come up a lot. What happens to the graph is if you zoom in on it. Well-behaved functions will look exactly like that. We zoom in and then it turns into a straight line. So in other words, it's something ideal. Well, look at if anything like that. If there is a virtual, not virtual, but actual infinite size corner on it, then when you zoom in, it's not going to have a straight line anymore. But those we will say, well, these functions are kind of poorly behaved, and we try to ignore them as much as possible. But by the way, the function is still continuous, but it has this cusp. So that's what makes it not as bad as discontinuous function, but still bad because the calculus breaks down. At this point, calculus breaks down on like a needle point, the end of the needle. Okay, so zooming in produces straight lines, and those straight lines are what we care about, one point at a time. But what if I go in the opposite direction? I go to and I zoom out. Okay. As you can see, what's happening to the function is once again function on the left, and the location function on the left, and the velocity function on the right. So, what do you see?
Is that the acceleration on the right?
No, that's velocity.
Velocity versus,
So the fact that
maximum velocity.
what?
It's got maximum velocity.
That's right. Yeah. So and then it starts to drop down slowly. So you slow down periodically. You speed up, slow down. So it's so much so that you look at that point where at around 3.5, it touches on the second graph. The graph of the velocity touches the x-axis, which means what? Velocity 0 on the graph, on the other graph. I wonder if I can...
The location stays the same?
Roughly, yes. Roughly, even though, so if I'm trying to overlap them, so this is the point. I align more or less the axes between each other. So wherever the velocity touches the x-axis means that it is 0, which means that the rate of change is 0, which means that there is at least for an instant, there is no change of location. Okay, so it's not, as you can see, it actually stops. If it does stop, it stops for a very short period of time, and then it keeps going in the same direction. But it could have turned around, and then, but that would make the velocity negative. So to demonstrate that, this velocity remains positive, as you can see on this picture. It remains positive for all this time because it never crosses the x-axis, the graph. If I change it slightly, so as you can see, what I have modeled here over here is x plus sine x. So how about something? Let me put a 3 here, just for fun. Okay, so it's almost the same, but you can see that the velocity now does cross the x-axis. The x-axis is kind of thin, but this is the x-axis, and we cross it. So what is this? Reverse. It's going in the opposite direction. So velocity negative means that the function, look at it, the location decreases. What does it mean? It means we're driving in the opposite direction. Well, I mean, this is probably not about driving, but whatever the object was moving, it is now moving in the opposite direction. Then it reverses again. And did I align them correctly? Almost. So you can see this close to 2. That's where the velocity is 0, and that's where a tip happens, or the highest point. So that's what the tip. It is as far as we went. As far as we went is on the y-axis here. So we did not pass that point, or at least at that time. We reached that point, stopped for an instant, and started to go backwards. Okay, and then once again over here, this is once again in alignment around 4.5 or whatever. Velocity is 0, corresponds to this point where as far back as we went, and then we stop for an instant and turn around and start driving forward again. Okay, so as you can see, the behavior the velocity changes periodically, as you can imagine that it keeps this pattern forever. So well, let's can you guess what the rest of, if I zoom out, what does this graph would look like? What if I put 10 here? What?
It look like stair steps, something like
Stair steps,
that.
yeah. With it will be, unlike the last graph, it will have dips. Let me put a 5 here. Yeah. The dip is almost invisible, but that's just because of the hold on a second, why is it because of the inaccuracy. As you can see, you need more points. As you can see, this one shows that as if the velocity never becomes negative. So well, that's inaccuracy. You have to be careful about that. As you can see, it is negative. H is just a step of period of time. So anyway, so that's just a demonstration, and some of the exercise, some of the projects are of this nature. Finding it's less likely actually in any kind of scientific or practical problems finding velocity from the location, but rather it's the opposite. You know the velocity, find the location, roughly speaking, or you know the acceleration and then find the location. That is really a typical physics problem. So you know force. From the force you know the acceleration according to one of Newton's laws, okay, and then from acceleration you find velocity, and then from velocity you find your location. So that's the physics problem. So a lot of them just like that, and you can pretty much model in that fashion. We'll get to that. This is just one direction, and then the essence of calculus is both directions. So from location to velocity, and then from velocity to location later, at some point. So this is going back and forth is the key thing, key to calculus in my opinion. Okay, so let's make it more slightly. Let's look at this last step now. So now we understand what we're talking about, but one thing to remember is the location, time, locations, velocity, and all this is just a starting point. It is either driving or physics. It's just a starting point, and if you were have anything feel for either driving or physics, then that helps you to have a metaphor or yardstick or whatever, just to test whatever new ideas of calculus come to you, and you test it against this idea, and then hopefully it gives you a way to understand it. But ultimately it's about functions, so the names here are not especially appropriate, so you have to leave it behind, and so you put variables here, say x for time, and then location y. Okay, and then, so what does it mean? It means that we have a function here, y equal f of x. Okay, so it is just a plot, a function, y equal f of x, two columns, and you plot them. And then velocity, what's velocity? Remember, there is no difference, it's the same. Look at it. Once again, two columns. Okay, so it is y equal f prime, called the derivative of this function, and it is not any more or any less than a function. So you produce a new function from the old, hence the word derivative. You derive one function from the first through this quotient. Okay, so let's talk about that quotient a little bit more. So given a function y equal f of x. Okay, so what we do with it, and it's also given an interval. So f is defined on it. Say a, b. Okay, and then we are producing a new function from old. Well, no, we are not producing a function just yet because these are fixed to begin with. So the average rate of change of f over AB is once again f of b minus f of a over b minus a. So change of y, just like in our spreadsheet, change of x. Okay, and we take the ratio. The plot, it is very, the meaning is very transparent. If I just, it doesn't matter what the graph looks like. All I care about is those 4 values, meaning 2 points. 1 point on the graph, and this is the other point on the graph. X, Y. So this is f of a, and this is f of b. Okay, so this is the numerator, numerator, yes, numerator, change of y, and this one is change of x. Okay, so, well, then let me just say that there's graph of function f here. What it is, we don't know at this point. Only these points matter. So these points are the only one taken into account. Just like with when we were driving and we were not looking at the odometer constantly. We only looked at it once in a while. So in the beginning of the hour and the end of the hour, and we took two readings, locations, and then certainly we also did some readings of the clock in order to do it, to compute the velocity. And similarly, we found this ratio, and now from this you can tell the meaning of this. Well, so the word already has come up. What is the meaning of this quotient? Okay, so this is the denominator and this is the numerator. So what are we talking about here?
The rate of change, the slope.
It is the slope. So so this is the rise and this is the run, and so the fraction is this fraction we're talking about is this is the slope, but not of the curve itself. As you look at that curve, that f of x and wildly behaving in between, going up and down, it's the slope of the line, straight line, through the 2 points a f of a and the b f of b. Okay, so all you have to do to make something more informative such as this, make more points, that's all. And that's roughly what you do is as follows. So that's the second definition related to this. Rather than doing one intro at a time, well, let's do all of them. So the difference quotient of y equal f of x with increment h is, let me just, okay, so it will be a fraction f of x plus h minus f of x over h. Just another way to look at it, it's the same thing as before, in the sense that I have 1 point here, this is x, and then I make a step forward and move on to x plus h, and then I have two values of y, f of x and f of x plus h, okay, And then once again, I have 2 points that the only ones that I care about. These are the points. Once again, I'm looking at nothing but a straight line through these. I am ignoring the rest of the function. What does it? So it's exactly the same as the last definition. What makes the difference is that it is a function this time. So h is fixed. It is just our step h, but it is actually, this thing is dependent on x. In other words, it's a function. Okay, so we produced a new function from the old function. Even before we are to study things, you know, well, it's not only, well, it is dependent on x and h. Okay, so in fact, it is for us to actually decide which the variable we actually care about. It depends on the circumstances. There are 2 variables simultaneously in play here. So one location. So we are looking at behavior, a function around x, and then how far we are prepared to go with that h. Okay, and the answer is for what we have been doing, we would fixed h and then did different axes all over the place. In the next step is actually concentrate on h and fix x and make h smaller and smaller and smaller and smaller, and take the limit and see what happens. Okay. So we'll resume next time.